Hi everyone. Today let's talk about Chapter 3, Section 3.1, Introducing the Derivatives. Big idea. To find the tangent line to a curve at the point on the curve, we can look at the limits of the secant lines as the second intersection points of the secants get closer and closer to the tangent point. The slope of the tangent line to a function at a point is called the derivative of the function at that point. Big skills. You should be able to compute the slope of a tangent line by taking the limits of the secant line function. You should be able to compute the derivative of a function at a point, or the derivative function in general, by evaluating the difference quotient limits, i.e. the limits of the secant line slope. Okay, so we call in section 2.1, we talk about average velocities and instantaneous velocities. So today we consider a curve, y equals f of x, and a secant line intersecting the curve at the points p of a, f of a, and q, x, f of x. So let's look at this picture. Let's say the first point we call A, and then the second point we call x. Okay? So the slope of the secant line we know is change of x over change of y, right? This is change of x, that is change of y, okay? So change of y is f of x minus f of a, and change of x is x minus a. So this is the slope of the secant line, is also called the average rate of change, okay? If we're talking about displacements, then this is average velocity. If we're talking about like population, then this is average growth rate, okay? So this is average rate of change of f on the interval from a to x. And the slope of the tangent line M tangent is the limit you let the second point x approaching the first point A. Okay, so you evaluate the limit x approaches a m tangent secant. Okay, so this is the limit x goes to a, f of x minus f of a over x minus a. Okay, so this is the first formula. Okay, the m tangent is also called the instantaneous rate of change of f at x equals to a, provided these limits exist. The tangent line at x equals a is the unique line through the points a, f of a with slope m tangent. Okay, so you can see this this red line in our picture is the tangent line. It's the line tangent to the curve at the point A. Okay. So if we want to write down the tangent line equation, well, we use point slope form. We have a point and we have a slope. Then we can use the point slope form. What is that? It's y minus the y coordinates of the points equals the slope times x minus x coordinates of the points. So this is our tangent line equation. Okay? And furthermore, there is another expression about the secant line and tangent line slope. Okay, so how does this work? You remember our picture? We called the first point A, and A is a fixed point, right? A is a fixed point, and the second point we call X, and it varies. That's why we set it as a variable X. Okay, so we have the second point is approaching to the first point, okay? And now I'm gonna call them a little bit different. So the first point I still call A, so it is a fixed point. But the second point instead of X, now I call it A plus H. Well, H is the difference between those 2 points. Okay, and you can see when H varies, the second point also varies. So this is like we're making a change of variable. X equals A plus H. Alright, so that's why f of x minus f of a now becomes f of a plus h minus f of a. right? But now, what is x minus a? Well, x minus a is just h. That's why the numerator now becomes f of a plus h minus f of a. The denominator is just h. Okay, so that's why the m tangent is remember when x goes to a, then it means the h goes to 0. Okay, so that's why m tangent equals the limits h goes to 0, f of a plus h minus f of a over h. So this is the second expression. And so we have two expressions. This is the first one. Okay, and this is the second one. Which one shall we use? I suggest you to use this one, the second one. Why? Because later on when we learn derivative, the formula is you just replace x in the second formula by x. Then you can get a general formula for the derivative. So because I want you to be consistent, because I don't want you to find the m tangent using one way and then find the derivative using another expression. I want you to get used to one expression, then you won't get confused. Okay, so I will recommend you to use the second expression. Okay, alright, let's look at example 1. Find the equation of the tangent line to the hyperbola y equals 3 over x at the point 3, 1. So in this problem, I'm going to show you using both expressions. Then you can compare and then you can see the difference between them. Okay? So using the first expression. Okay, so first, okay. Using the first expression, m tangent is limit x goes to a. So in this case, a is 3. Well, what is 1? 1 is actually f of a. Well, you can plug in it. What's f of a? Is 3 over a is 3, so it's 1, right? So x goes to 3, and then f of 3 minus, sorry, f of x minus f of a, which is 3, over x minus a, which is 3. Okay, what is it now? F of x is 3 over x, right? F of 3, that means whenever you see x in the expression, you plug in 3. So that's 3 over 3. And let's continue. So we get 3 over x minus 1 over x minus 3. Do you remember when we compute limits? First step, we plug in, x goes to 3. So first step, we plug in the x value. So 3 over 3 is 1, 1 minus 1, 0. So you see we get 0 over 0. That means there is a back guy, right? So what do we do? Because it's fraction, so we don't want to see a fraction in a fraction. So that's why we take the common denominator x, then we have 3 minus x. Okay? And here, let's simplify it. Remember, a over b over c over d is a over b times d over c. So we have 3 minus x over x is like the b, stay downstairs. X minus 3 is like the c, so it stays downstairs. Can you see the bad guy? Oops. So be careful here. We cannot cancel them yet because 3 minus x and x minus 3, they're not exactly the same thing. So how do we make them the same? We switch the, okay, so we can factor out minus 1 here, then we get x minus 3. And x minus 3. So now we have them exactly the same. We can cancel it. So now we get minus 1 over x. We plug in x is 3. So then we get minus 1/3. Okay, so this is m tangent. And then How do we find the tangent line? Well, the tangent line equation, we need the points. We also need the slope. Do we have the points? Yes, that is the 3, 1, right? Do we have the slope? Yes, that's negative 1/3. So the tangent line is y minus the y coordinates of the points equals the slope x minus the x coordinates of that point. So we have y minus 1 minus 1/3 x. Distribute it, become positive 1. So we solve for y. We both sides add 1. Okay, then we have plus 2 here. So please express your tangent line in the slope-intercept form. So this is a slope-intercept form. Okay, so for all of your homework problems or your exam problems, when I ask you to find the tangent line, please express your answer in terms of the slope-intercept form. Because the point-slope form is not unique. So different points, we get a different point-slope form. But after you express it in terms of slope-intercept form, this form is actually unique. Okay, so for all the lines, please express in terms of slope-intercept form. Okay, so this is the first method about finding the slope. We have a second method. Okay, second expression. And tangent is, so h goes to 0, f of a is 3, a plus h minus f of a all over h. Okay, so this is the formula. And what is f of 3 plus h? Well, that means whenever you see x, we place the x by 3 plus h. Okay, it's we place, whenever you see x, we place it by 3 plus h. Minus f of 3. F of 3, we know that's 1 over h. Well, you see we have fraction in the fraction. So let's take the common denominator, 3 plus h. Then we have 3 minus, here, you gotta be careful. If we have 1, how do we get this common denominator? We multiply by 3 plus h. But don't forget your baby parentheses. Okay, so parentheses is so important, don't forget that. And then we have fraction and fraction, so a over b over c over d is a over b times d over c. So the top 3 minus, let's break the parentheses. So it's minus 3 minus h. 3 plus h is actually in the denominator. H is actually in the denominator. Now, can you see the 3 cancel? So we have minus h over 3 plus h times h. Now, can you see the bad guy? Yes, the bad guy is h. Okay, so after we cancel it, we get minus 1 over 3 plus h. And now we are safe. We can let h be 0. Okay, then we get minus 1/3. Do you see this answer is the same as the previous method? Yeah, we always get the same answer. Let's compare both methods. The good thing about the second method is your h is always getting close to 0. So your bad guy is always h. But in the previous case, if your a is different, then the bad guy is x minus a. So if your a value is different, then that factor is different. Okay? So, and then the steps how to find the tangent line are the same. So after you get the slope, then you plug in your point and slope to get the point slope form, and solve for y to get the slope intercept form. So far, so good, everybody? Alright, let's continue to look at example 2. So example 2, I also want to solve it in both expressions so that you can compare and see the differences between them. Okay, so yeah, I would like to show you different ways of solving a problem. Okay, Alright, so method 1. We want to find the tangent line to the parabola at x equals 2. So m tangent is the limits x goes to 2 f of x minus f of 2 over x minus 2. So f of x is, well, our function, right? F of 2, well, what is f of 2? Well, then you plug 2 into the function. What is that? Well, let's find it here. So that's 2 times 2 squared minus 5 times 2 plus 1. 2 squared 4, 2 times 4, 8, minus 10 plus 1. So it's negative 2 plus 1 is negative 1. So far, so good, everybody. And let's see. So here we have 2x, so minus negative 1 over x minus 2. And then minus negative 1 is the same as plus 1. So this is the same as 2x squared minus 5x plus 2. Okay, so then next, what do we do? Well, when you plug in 2, you realize we get 0 over 0, but because we have polynomial, it means we can factor it, right? How can we factor it? 2x, x, negative 2 and negative 1, right? So this is how we can factor it. Now, can you see the bad guy? Yes, x minus 2 is the bad guy. And now we can plug in the 2 again. 2 times 2 is 4. 4 minus 1 is 3. Okay, so this is how we find the slope of the tangent line using the first expression of our formula. Okay, how about the second expression? M tangent is limits. So don't forget, you have to put the limits all the time in all the steps whenever you see the variable. Okay, so this is f of a plus h. So 2 plus h minus f of 2 over h. Well, 2 plus h is, so 2 plus h, whenever you see x, replace x by 2 plus h and the parentheses. Square minus 5, 2 plus h, plus 1, and then minus f of 2. F of 2 is negative 1, okay? All over h. Okay, so 2, and then 2 plus h squared is 2 squared, which is 4, plus 2 times 2, 4h plus h squared. Yeah, you guys gotta be careful. And then when we distribute, that's 10, and that's 5h, and then plus 2. So far, so good, everybody? Okay, all over h. And then next, we distribute. So 2 times 4 is 8, plus 8h plus 2h squared minus 10 minus 5h plus 2. Okay, now let's see. So 8 and 10 and 2 cancel. So how many h squared do we have? 2h squared. And then 8h minus 5h is 3h. Now you see all the numerator, they have a common factor h. So we can factor that out. Then we have 2h plus 3 all over h. Now you see the bad guy. After we cancel the bad guy, we get 2h plus 3. And then when h goes to 0, this is 3. Do you see we have the same answer? Okay? You might think, oh, isn't it this way? It looks easier than the second method. I will show you later if you want to get a formula of the derivative f prime of x, you want to have a function of x, you're gonna use this formula anyway. Okay, so the second expression is more general, and it also works when you find the derivative in general. So that's why I suggest you to use the second method. Okay, so after you find the slope, we haven't done yet, right? We also need to find the tangent line equation. So what's the tangent line? Y minus the y coordinate, which is -1, equals to the slope 3, and then x minus the x coordinates 2. So y plus 1 equals 3x minus 6. Subtract 1. So this is the tangent line. So far, so good, everybody? Okay, so next, let's continue. Well, the derivative of f is the function f prime of x that equals our second expression. And instead of a, now we let a be x. Okay, so how do we call them? Well, the first point we call x. Well, the second point we call x plus h. Okay, then the derivative is the limit of the change of y over change of x. Change of y is f of x plus h minus f of x. Change of x is the difference between those 2 points is just h. Okay, change of x is h. So far, so good. If the derivative exists, we say f is differentiable at x. If f is differentiable at every point of an open interval I, then we say f is differentiable on the interval I. Okay, and here we have a lot of expression, but they all mean the same thing. Oh, here, I forgot the equal sign. So the derivative of f equals the limit change of x goes to 0, f of x plus change of x minus f of x over change of x. That also equals limit change of x goes to 0, change of y over change of x. And if the change of x is getting close to 0, we get the differential. So that equals dy over dx. So dy and dx, their differential is like they're the change of y and change of x. But now when the change is smaller, then we call it differential dy and dx. And here are all the notation of derivatives. They all mean the same thing. So you can write f prime of x, you can write dy dx, df dx, d dx of f of x. So here we are like considered the differential is like an operator. When you add on the function f, you get the derivative d dx of f. And we can also use this symbol capital D small x, d sub x. This also indicates the derivative, okay? And you will see this symbol more in calculus 3. So here we're in calculus 1, we're talking about the calculus of one variable. But in calculus 3, we talk about multi-variable calculus. And then d sub x, this is a derivative with respect to x. You might have d sub y, this is partial derivatives with respect to y, or d sub z, okay, partial derivative with respect to z. So instead of one variable, we will talk about 2 or 3 variables in calculus 3. Okay, and we can also have y prime of x. Okay, so all of these, they are derivatives. How about the notation for the derivative at a point? We can have f prime of a. We can have the derivative evaluate at x equals a. So you see that this vertical lines, it means evaluate at. Okay, we can have df dx evaluate at x equals a. We can have y prime of a. So all of these different notations that just represent the same thing. Okay, everybody? So if you see different notation in our examples, don't be surprised. Okay? Next. Find the derivative of y. Okay, so how do we find the derivative in general? So we only have one formula, just like the second formula. F prime of x is the limit h goes to 0. And then f of x plus h minus f of x over h. So this is the formula we use. What is f of x plus h? Well, look at our function. Whenever you see x, we place x by x plus h. So we have square root 3. Well, the x, we place x by x plus h. But don't forget your parentheses. So it's like you replace the whole thing by parentheses x plus h. Okay? So be careful. Don't forget the parentheses. If you forget the parentheses, then that's wrong. And minus f of x is just 3x plus 5, right? All over h. Okay, what is this guy? Okay, so let's distribute. This is a 3x plus 3h, right? So 3x plus 3h plus 5 minus 3x plus 5h. Okay, so when we try to plug in h is 0, we get, the numerator when we plug in h is 0, we get this term and this term, they're just the same thing. So we have 0 over 0. 0 over 0 means there is a bad guy, right? But how do we continue? So when you see difference of square roots, what do you do? What do you do? Do you remember? We multiply by what? The conjugates. What is the conjugates? Well, it's almost the same thing. But we place the middle sign by plus. Okay. And when you multiply by something, you also need to divide by the same thing. So you're not changing anything to the term or expression, right? Okay, now after we do that, then the numerator becomes, remember, a plus b, a minus b is a squared minus b squared, right? So that helps us to get rid of the square roots. So a squared now becomes 3x plus 3h plus 5. And then b squared is 3x plus 5. Is that right? No. Don't forget your baby. That's why your baby is so important. Sometimes you realize you don't get the answer because you might forgot your baby in the mall. Okay, so don't forget it. Alright, so now what can we do? Well, we can continue and distribute. So become minus 3x minus 5h and then this guy. Okay, so now can you see we can cancel a lot of things? We can cancel the 3x, we can cancel the 5. And what's left on the top, you see, is only 3h. So, here, if you had a mistake, then you will realize you're not able to cancel the 5. And then, you should always get an h in the numerator after you cancel everything. Okay? Because that's the bad guy, make the numerator and denominator 0. So you should always have the h. Because now you can cancel the h, then we are safe, right? So we are safe, and because we let h goes to 0, so we have 3 over, this is square root of 3x plus 3h plus 5 plus square root 3x plus 5. Now we let the h goes to 0, so if this guy goes to 0, do you realize this term and this term, they're the same thing? So because of the same thing, we get 2 copy of the square root of 3x plus 5. So this is our solution. Okay, you can see the result is a function of x. So the derivative is the function of x. Okay, so in the previous example 1 and example 2, to 2 different formulas, we will get a number because this is the derivative evaluated at 1 point. So we get a number. But now we use this formula and we solve it, and the result is a function of x. The derivative is a function of x. It tells us it talk about the slope of the tangent line at different points of the function. Okay, let's continue. So example 4, show that f of x equals absolute value of x is not differentiable at x equals 0. Okay, so it's not differentiable by 0. Let's figure out what's wrong. Okay, let's compute. H goes to 0. Okay, we want to compute that, and we want to have f of 0 plus h minus f of 0 and over h, right? So this is the derivative. Let's try to compute and let's see what happens. F of 0 plus h. Well, that is 0 plus h, right? Minus f of 0. Oh, that's absolute value of 0. Okay, what is that? Oh, this is absolute value of h minus absolute value of 0 is 0, right? So we get this. Okay, what's the problem? It really depends on whether h is positive or h is negative. Because when h is positive, okay, then absolute value of h is just, so here, because h is positive, absolute value of h is just h. Well, h over h, that's 1, right? But on the other hand, when h goes to 0 from the left, because now h is negative, then if h is negative, absolute value of h is minus h. So that's why, we get minus 1. You see, they're not equal. If the two sided limits do not agree, then this guy does not exist. Okay, and we can draw the picture of absolute value of x, what it looks like. Okay, this is the picture of absolute value of x. And you can see on the left hand side, the slope is 1. On the right hand side, the slope is negative 1, right? The slope is negative 1. You can see they don't match at the 0. So that's why it's not differentiable at the point 0. So far, so good, everybody. Alright, let's continue. So what is slope mean? So slope of the tangent line will give us the derivative of the function, right? So example 5, we want to use the graph of a function to sketch the graph of the derivative f prime. Okay, so what is the slope? Well, we know that the blue line is our function f, right? And we want to find the derivative f prime, okay? So first of all, we want to look at this point. You can see this point 8. You see the slope of the tangent line is 0. Okay, so that means if we want to draw the derivative, okay, the slope is 0. So we have the same x value, but the y value is 0. So we plot those x-intercepts here. And then point B, you see at point B, the slope is also 0. So we have the same x-intercept, but the y-coordinate is 0. So we also put a point here as well. And point C, we also have 0 here. And then point P, you see the slope is approximately 3/2. Where's 3/2? Well, that's 1.5. Well, this is 1, this is 2, 1.5 is like here. So we have the same x value, but the y value is approximately 1.5. We plot those dots. Now, after we put the dots, we should connect the dots smoothly. And let's look at each pieces. Well, this pieces, what's the slope? The slope is positive or negative? Remember, this guy is positive, this guy negative, this guy 0, this guy undefined. Okay, so here, the slope is negative, so which means negative is above the x-axis or below the x-axis. Below, right? So, and this piece is below, so like this. And how about when we connect those 2 points? Well, look at this region. Is it increasing or decreasing? You can see the slope. The slope is actually positive, right? So that's why we connect them and it's above the x-axis. How about this piece? Well, this piece, you can see the slope is negative. So that's why the derivative is below the x-axis. And when we connect these 2 points, you can see the slope is positive. So that's why it's above. And we connect them together. So the green line is the derivative. Okay, it's the derivative of the tangent line at each point of the function. Okay, so let's summarize our rules. Remember, when we see a different kind of problem, I would like to summarize the rules with you. Okay, so first, we want to find where the slope is 0. Okay, and then we can draw the x-intercept. Okay, that's the first step. Well, the second step, well, you depends on whether it's positive or negative slope. If our slope of f is positive, okay. By the way, slope of f is the same as f prime, right? Okay, so slope of f is the same as f prime, okay? So if f prime is positive, how do you draw it? Well, because it's above the x-axis, so you connect those points above. When the slope is negative, what do? You connect those points below the x-axis. So far, so good, everybody? Okay, so this is about the graph and the graph of the function and the graph of the derivative. I also want to show you our GeoGebra projects. So our first GeoGebra project is using GeoGebra to verify derivatives as the slope of tangent line, and I give you a PDF instructions. So here, you're gonna go to this website and download GeoGebra Classic 6. So click this website. You see there are 6 of them. So download the GeoGebra Classic 6. Okay? And then you can watch this YouTube video. So I have a YouTube video teach you how to draw the GeoGebra project. Okay? So this is my YouTube video and I will show you. And then next, I also give you a screen by screenshots and to teach you how to graph those projects. Okay, so after you're done, please share your project to public and email me the link. Okay, you will get a link and then so email me the link. So the GeoGebra project's worth 0.5% extra credits. Okay, so this is the projects I make. All right, you can see the green line is the function, and then when I let the points move around, you can see the slope. Okay, so all right, so you can the yellow line is the derivative. So the point B actually plots the slope of the tangent line. Okay, so you can see the slope, the point B, the slope of the tangent line really match the derivatives. Okay, so we have more examples here. So you're gonna make an example like this and then email me the link. Please be creative and make different functions. Okay, so this is the exponential functions. You can see the functions actually is the same as the derivative. Yeah, exponential function is quite special because the derivative is itself. And we also have more. This is sine x. We will learn that sine x, the derivative is cosine x. So you can see the green line is the function sine x. The derivative, which is the yellow line, that is actually cosine x. So we will show that later in session 3.4. Okay? And you can see the point B represents the slope of the tangent line. It really matches the derivative. Okay, and so let's continue. Relations between continuity and differentiability. We have a theorem. If f is differentiable at a, then f is continuous at a. Contrapositive version. If f is not continuous at a, then f is not differentiable at a. So are you familiar with logic? So if we have a statement P implies Q, if this is true, then not Q implies not P is also true. Okay, so this guy is called contrapositive statement. So this is like P is differentiable at A, Q, F is continuous at A. So if P is differentiable at A, then F is continuous at A. So this is P implies Q. Okay, if P is not continuous, so this is like not Q, okay, and then that implies not P, F is not differentiable at A, okay. However, the converse is might not be true, okay, actually it's not true. If a function is continuous, it could be not differentiable, okay, yes. Continuity does not imply differentiability. For example, square root of x looks like this. You can see it's continuous, but it's not differentiable. Okay? So when is a function not differentiable at the point? So we have actually three types. Okay, first type, when the function of f has a corner or a kink in it. Okay, so like here we have a corner, so then it's not differentiable. In this case, you will see the left side limit does not equal to the right side limit of the derivative. So the derivative at that point does not exist. Okay. Second one is when f is not continuous at a. So if it's not differentiable, then of course it's not continuous by the theorem. Okay, and how many different type of discontinuity? We can have removable discontinuity, we can have jump discontinuity, we can have infinite discontinuity, and essential discontinuity. Okay, and then the third type, when the graph of f has a vertical tangent line at 8. So that is like this picture. We have a tangent line, but it's vertical. Well, in this case, the slope does not exist. So we know the derivative is the slope of the tangent line because the slope of the tangent line does not exist at that point. So the derivative does not exist. So that's why here are the three types of discontinuities. We can have a corner, we can have a discontinuity, we can have a vertical tangent. So all of those three types are not differentiable. Okay? And then example 6, we want to match the graph of each functions with the graph of its derivative. Okay, let's look at the first one. If I hide this graph, can you figure out the derivative by yourself? Let's see. So this guy, we look for the point where the slope is 0, right? We know here the slope is 0. Then we plot the x-intercept. Here the slope is 0. Oops. And we plot the x-intercepts. And this piece, the slope is positive or negative. we can see the slope is negative, then which means the derivative is below the x-axis. And this piece, the slope is positive, so the derivative is above the x-axis. And then this piece, the slope is negative, so it's below the x-axis. So which one looks like that? Oh, this guy, right? So the number 2 match. How about this one? Well, this is because there's line segments. So this guy, the slope is positive and it's constant slope. So that's why we have constants. And then we're not differentiable at that point, but this slope is negative. So it could be like that. Here, this piece, the slope is positive. So we are here. Number 4. Okay, next. Well, next you can see here, this guy, the slope is 0, and this guy, the slope is negative, right? But when you're getting close to infinity, it's flat, so the slope is getting close to 0. So this piece is negative, but getting close to 0. So like that. This piece is positive, but it's also getting close to 0 when x goes to infinity. So positive means above the x-axis and getting close to 0 when x goes to infinity. Ooh, this is picture 1. Okay. Oh, next one. Oh, this looks like a T, right? So we find the point where the slope is 0. So we plot the x-intercept, and then each piece, this guy, the slope is positive, so we are above the x-axis. This piece, the slope is negative, so it is below the x-axis, and we connect those 2 points together. And then this piece, the slope is positive, so it's above the x-axis. This piece, the slope is negative, so it's below the x-axis. So we have this picture, number 3. Okay. Oh, let me draw it more smoothly. Okay. All right. So far, so good, everybody. Okay, let's continue. Example 7. State the numbers at which the following functions are not differentiable. Okay, so let's look. All right. So this guy, you look at here, we have a corner, right? So it's a 1, 2, 3, 4. So this is -4. The first picture, this is not differentiable at x equals -4. And what is the type? We have a corner at there. So far, so good, everybody. Oops, so we have one more. We have a corner here. Okay, next, you see at 0, we have discontinuity there. So discontinuity. Okay, so we have discontinuity there, so it's not differentiable. So far, so good. Let's see here. It doesn't look like a vertical tangent, so I don't think there's a vertical tangent there. So we can leave there. Okay, how about this guy? Oh, we have discontinuity as well, okay? Oh, by the way, the previous one is jump discontinuity. Okay, so here x equal to 0, we have infinite discontinuity. Okay, and then this guy, we have a corner, so F3, we have a corner. So far, so good, everybody. And let's continue. Well, here, you see here, I have a vertical tangent. So x equals -1, we have a vertical tangent. And here, when x equals 4, we have a corner. So far, so good, everybody. And then here, when x equals -1, we have a jump discontinuity. Okay, and when x equals 2, we have a corner. Alright, so this is how we can find the discontinuity, and we can classify the types of discontinuity. We can have a corner. Okay, we might have a discontinuity, and then for the discontinuity, you also need to classify the type of it. We can have removable, jump, infinite, essential discontinuities. And the third type is when we have a vertical tangent. Okay, so that is session 3.1. Have a good day.